Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and as always, welcome to the podcast. So on today's episode, I was asked if I would do a little episode on understanding current carrying conductors, most notably when you're applying them to an application where you need to know the number of current carrying conductors, especially if you're applying the rules in 31015B3A and all those type of goodies. One of the things that people ask me all the time is, Paul, what do I really need to, not necessarily when we're talking exam, okay? Although, you got to know these things. One of the things that I get people that ask me is, when I'm applying things like 31015B3A, which is an adjustment factor where you have more than 3 current carrying conductors, well, how do I know when I got more than 3 current carrying conductors? And I'm like, well, most of the time, if you have an apprenticeship program or you have something you worked with, you kind of get a good understanding by the time you're into your 4th year of when I apply it and when I don't. But I routinely get these conversations with people who will call me and say, Paul, how do I know? And, I could say, well, you can get a good understanding, or at least the basic understanding of going into the code and go to 31015, and go to B, B5. I'm not sure. I might as well crack my code book with you and make sure. Yes, B5. And let me make sure, yeah. And you look at that. I should say, we're in the 2017 edition of the National Electrical Code. We're actively involved in the 2020, but we're talking about the most recently adopted, and at this stage, we're dealing with the 2017 edition. So when you go to 31015B5, which will change in the 2020 code, but that's a whole different story, it tells you right away. It says Neutral Conductor. And when we see that, it's really important to note that the NEC refers to current carrying conductors for the purpose of derating when there is more than 3 current carrying conductors in a raceway or cable. So you have these basic rules that are going to apply. And I wanted to take an episode to kind of look at those to help somebody maybe understand the basics of it and discuss it that way. Okay, now, first and foremost, the term, as you see me throw around, the term derating, it's been used by many people. It's been used for a year. It's really not something that's in the NEC. Really what we have is adjustment and corrections. But collectively, we like to put those together and call them, derating, meaning that some other conditions got to take place to reduce, and I like to keep it simple, reduce the current carrying capacity of a conductor based on the condition of use, whether it's the temperatures that are involved, the ambient temperatures, which are going to cause it to actually be corrected. And if we have to correct it due to that, then we have to understand that we need to apply 31015B2A because that's an ambient temperature correction. And then, of course, if we have the certain number of current carrying conductors, and again, we're going to talk about what constitutes a certain number, then we're going to have to do what's called an adjustment. Together, for people to keep it from getting confused, I guess we use the term derating, and it really doesn't matter because I hear all the time, and I'm guilty of it. I'll talk about adjustments when I'm dealing with temperature, and when I'm temperature, I call that, which is supposed to be a correction, and when I'm dealing with the number of conductors, I'll sometimes say correction, which is actually an adjustment. I think at the end of the day, we know what we mean. And so when we say derating, we really know that we're taking a base value, which is really the ampacity values, because, that's what we're here to do, right? We're trying to adjust or correct some base value. And in 310.15b16, which is our ampacity table, it is all based on some conditions. And the condition is we don't have more than 3 current carrying conductors. And the base ambient is 30 degrees C or 86 degrees Fahrenheit. So anytime the condition of use means whatever's going on in the location or where you're putting this wiring method and the associated conductors, wherever it is, there's something that deviates from the baseline. And that is you'll have more than 3 current carrying conductors, or the temperature values will be above or below the base ambient that's given to us in 310.15b16, right? So we all can agree on that. Now, in the perfect world, you pull straight from this table, and you're still going to use this table because this is going to give you the allowance to use possibly the 90 degrees C ampacity value for that adjustment or correction. It really depends if that conductor is rated for 90, or even if the terminals are rated 75, which typically they're going to be 60, 75. There's very few 90 degree rated terminals. They do exist, but very few. So typically motors and things like that, you're going to default into 75, and in most things like circuit breakers or whatnot, it's going to be 60/75. So most of the time when we're teaching exams, we typically stick at the 75. However, if I'm using a conductor with an insulation rating that's good for 90, then the code allows us in 310.15 to be able to use that benefit, if you will, of a higher ampacity value and do our adjustment and corrections against that value, which is going to obviously lower that ampacity. And then once we do that, we have a new ampacity value on that conductor, taking into all these considerations. And then we have to compare that to the termination. And that's where 110.14c, 1 or 2 come in, depending on what markings are on the conductors, the terminal ratings, and all that. If all of that's confusing to you, rather than rehash all that again, because I want to kind of stick to our topic, which is understanding when a neutral is considered current carrying or not, I'm going to encourage you to go watch our video on derating demystified, because I kind of go over the overcurrent protection, how to protect the conductor, the concept of it, and all of that. And it's over an hour, and we've already spent a lot of time dedicated to that. So I want to encourage you to go do that. Go to our YouTube channel if that's where you're listening to this podcast. If you're on Spotify or iTunes or whatever, then just go to masterthenec.com. Up at the top, you'll see a little button, like a banner, that says our YouTube videos. Click on that. The reason you don't want to use the video tab on the website is because I don't update that as current as it is on the YouTube channel. Okay? And most of our listeners actually don't listen through the YouTube. The listeners for the podcast listen through the podcast link on our site, or one of the, like Spotify or iTunes or FM or one of those, iHeartRadio. They listen that way. So, we have to use a third party to track the analytics to that, because it would be easy if they all went to YouTube, but they don't. Okay. So, however you choose to listen, if you want to see the current videos, then you got to go to the YouTube channel, because that's where we put everything on the YouTube. That's our video host, if you will. So anyway, if anything deviates from 310.15b16, then you're going to have to do some kind of adjustment and correction. And of course, that's where 310.15b2a and b3a come into play. Okay, not generally the topic of the day, but I just want to kind of give you that overriding foundation so that we can end up coming back and talk about neutral conductors. So in your National Electrical Code book, if you're following along, you're pausing, whatever, catching up, then you really want to go to 310.15b5. Now, that consists of an A, B, and a subpart, A, B, and a C. Okay. The first one is dealing with, and we'll talk about it, where you're dealing with a neutral conductor only carries the unbalanced current from other conductors. And I'll kind of give you an understanding so you kind of get it. The next one we're talking about is a 3-wire circuit consisting of 2-phase conductors and a neutral. And it's actually making connection onto a 4-wire 3-phase Y-connected system. Okay. And then, of course, the The third one, C, is dealing with the same kind of concept. It's still a Y system. However, this is not a derivative where we're pulling 3 wires off of a 4-wire 3-phase Y. This is literally a 4-wire 3-phase Y system in its existence. But it's feeding a system where you have a lot of nonlinear loads and harmonic currents. And we'll kind of touch on that a little bit. But I am very cognizant of the fact that I don't want to take it. I want to keep it at the 30,000 foot view. If you have any questions on any of these topics more in depth, like harmonic currents and whatnot, you always are free to email me and reach out, and I'll explain those in detail if you feel the desire to know it more. Most electricians I know, electricians want to know the basics. Engineers want to know the more details on what's considered a nonlinear load or harmonic currents, whether it's tripling harmonics, which are the most effective, or I should say the most detrimental to the system. But, obviously we can go into that in another podcast, so I want to keep it these as short as I can, and everybody knows I'm long-winded anyway. All right, so let's kind of go back to 31015B5 and look at neutral conductor. Let's look at the first one. If you're following along in your code book, on the PDF version, which I use a lot, is on page 151. If you're in the printed version, then it's going to be on page 148, okay, is what we're talking about. All right, again, we're trying to determine when a neutral conductor is going to be considered current carrying, so that we know that when we apply the values, for example, in 31015B3A, does that conductor count when we start to get to that over 3? So we have to do some kind of adjustment to the ampacity value of these conductors because, again, you got mutual heating from the other conductors. It is carrying current, and it can be an issue. Okay, so in a lot of those other aspects of it, because of how the system is set up, the neutral conductor can carry equal to the same amount of current as the ungrounded conductor, and that generates heat. Whereas in a system where it's only carrying the unbalanced current, then it's probably not going to peak the same as the phase, and so it's not going to generate the same level of heat, so it doesn't have to raise the same level of caution, if you will, keeping it as simple as I can explain it on a podcast. So let's look at A. In A, again, we're talking neutral conductor. So it says a neutral conductor that carries only the unbalanced current from other conductors of the same circuit shall not be required to be counted when applying the provisions of 31015B3A. All right, pretty straightforward there, right? So what's the easiest example that I can say on this one? Okay, what about service conductors coming from a meter? And let's just use plain old SE style U. It's got 2 ungrounded conductors. Could be black and red, could be 2 blacks, doesn't really matter. Coming in, and it has either a helical wrapped grounded neutral conductor that wraps around it. So we're pretty much familiar with what an SEU is. It looks like non-metallic sheath cable. It is a non-metallic product, but it's really only got 3 conductors in it. And so now the standard UL 854 would allow it to not be helical. It could be just a conductor in there, stranded conductor, typically just like what you're going to get on the ungrounded. But most of the manufacturers of wire and cable will produce it in the U style because it's only got 3 conductors. They will produce it in that U style. And in that case, what you do with that helical is once you get it into the box or the cabinet, you then twist it together and you spin it a little bit, and that creates your own conductor, if you will. You bring all of those strands together and then you terminate it in a terminal. All right, but the key here is you have a line 1 and a line 2, or you could say phase A, phase B, whatever you want to say. I tend to say phasing, which is back at the transformer, but we all know that as extension of the transformer, it comes out into this panel. This line A and line B, or line 1, line 2, whatever you want. These are ungrounded conductors. And in this scenario here, the imbalanced or the unbalanced current is going to be traveling on that neutral conductor. So if I have 50 amps on leg A, whatever the load would be in that panel, and I have 50 amps on B, a very balanced out panel, by the way, if that was the case, then the neutral conductor is only going to see the unbalanced current from the other conductors. So it's 50 on one, 50 on the other. The neutral's going to see 0. So you don't have that heat buildup. You don't have the application where that's going to contribute. Okay? So if I have 100 amperes on leg A and I have 50 amperes on leg B, then the only thing that we're going to see on the neutral is the unbalanced current on that, which would be 50 amperes, because I've got 100 on A and 50 on B. So the return current is going to be 50 amperes on the neutral. Now, a lot of times that confuses people, but it has to do with the sinusoidal waveform and how it's at the peak on the upside, and then how the other phase is at the lowest portion, or the drop peak, I'll use these words loosely, in the waveform, and it serves as a kind of a cancellation effect that takes place, right? So if it was 50 and 50, you have 0. If it's 150, you have 50. That is what the unbalanced current would be. That doesn't get canceled out. And so that's what's going to return, because we always have current traveling to and from the load on a circuit. In order for the circuit to work, it's got to be a complete circuit, right? So you have that complete closed circuit. When somebody flips on a switch, then you're opening the circuit, okay? So keeping it very level into that concept. So that's what we've got. Now, another example of this would be a pure multi-wire branch circuit, where we're going with let's say we're dealing with an NMB, which is let's say, just for argument's sake, a 14-3 with a ground. So I have a black, a red, a white, and a bare equipment grounding conductor. And it's going out to, and it's in a panel, and it has a 2-pole breaker or 2 single-pole breakers with an identified handle tie. The whole concept is to keep them side by side so that one side of that breaker is being fed from phase A, and the other of that 2-pole breaker is being fed from phase B, so that we can take advantage of that cancellation. Well, and that's the case, then I have one circuit, and each one of them do get qualified as a circuit, even though it's called a multi-wire branch circuit. Each one of them qualifies as a individual branch circuit. They're just simply sharing a neutral. And so when it goes out, it's the same concept. If I have 10 amps on one, on the red, and I have 5 amps on the black, then as we know by now, the unbalanced current is going to be 5 amps traveling back on the neutral. And so in that scenario, I do not have to count that neutral conductor as a current carrying conductor. Okay? So that's what 5A is telling us. And we want to keep it just that simple right now, so that you kind of don't get lost in the weeds, but that's what it's dealing with. Okay? So multi-wire branch circuit applications, that's what we got going on. And then, of course, service conductor applications, where we have line 1 and line 2 coming in, and we have maybe you're using type SCU and that type of scenario. Okay. Now, the same concept would be if I was going from that panel to a remote distribution panel. Many people call it a sub panel, but it's technically it's a distribution panel downstream. And we're all familiar with the fact at that point we have to switch over to 4 conductors, so we have a separation between the grounded and the grounding, so that we have what we call a floating neutral on the load side of that service equipment when you get to that remote distribution panel. And it's not theoretically floating. It still gets connected and it's attached to the enclosure, but it's isolated away so that we don't have neutral current, which we know is flowing on the circuit at all time. It's going to be definitely carrying the unbalanced current. We don't want it coming back on the metal parts, but we do want to make sure that downstream that we have an equipment grounding conductor in case any of that metal enclosure gets energized or any of those unphased conductors fault out to the equipment grounding conductor or the metal parts, that we do allow current to travel back so that at that fault location, it elevates the level of current that takes place because of the low impedance ground fault current path back, because we tie all this stuff together really well, that we're going to trip a breaker. And so, but we don't want an active circulation of current on all these metal parts. We want it to be an accidental event that happens due to something taking place. And that's very much part of the safety aspect of how the circuit operates. Whereas we know that current always traveling on the neutrals at any given time, generally speaking. A totally purely balanced three-phase load might have nothing traveling on the neutral, but we're going to keep it very general here. Most of the time, you're not going to get something that balanced out, so you'll have neutral current. Now, you could have a motor or something downstream that is three-phase that you don't even take a neutral to because you don't need it. And if that's the case, that motor's been designed to be balanced out because of how the separation or the phases are out of phase 120 degrees. Then at the end of the day, what you run into is an aspect of not needing the neutral. So, obviously if you have no neutral in those applications, you don't count it as a current carrying conductor because there isn't one there. Anyway, that is really more than I want to get into in this episode. All right, so downstream panel, the neutral is kind of floating, if you will. It's isolated away from the enclosure, but that equipment grounded conductor does terminate on the enclosure in case all those metal parts do get energized by some reason. Then it can trip a breaker. Okay. So that case scenario is that'd be like an SCR, service instruments round, where it's got a black, a white, or a red, and a bare or insulated equipment ground. Doesn't have to be insulated. Could be. Whatever manufacturer chooses to do that. Incidentally, when we put a bare conductor inside of a cable assembly like that, it's called covered. Okay? It's not bare. It is bare as a conductor, but when we refer to it as a cable assembly, it's covered. Okay? It's really important if you go into 680 and you understand what the term covered means in some of those applications. But we put it inside of there, and it's a covered bare conductor. But of course you could insulate it if you wanted. That's totally the choice of how you buy your product. But most of us manufacturers, it's just going to be bare in an SCR. So anyway, that going downstream, again, that neutral is carrying the unbalanced current from line A and B. And so that's the application. Okay. More often than not, that is, again, the low-hanging fruit and the fact that is usually single-phase application. So it kind of makes that easier to understand. That does not mean you can't have a purely neutral conductor in a three-phase circuit. We're just going to talk to you about some conditions where you don't have a neutral in a three-phase application. All right, and so we're going to talk about that obviously here in a second. Okay. All right. So at the end of the day, let's kind of talk about when we have a neutral conductor and when we don't. Just get me back on topic. Okay. Now, again, when we're dealing with 5A, is you have to understand when you do and when you don't. Okay. So, I guess I should spin it back a little bit and talk about current carrying conductors a little bit. Yes, you do count current carrying conductors when the conductors are running parallel. Okay. So parallel conductors are two or more conductors that are connected at each end and are a cheap way to do it in order to get more current. So we run parallel applications. Remember that neutral conductors minimum size is going to be 1 aught. Okay, and we find that rule in 310.10h when it comes to paralleling conductors. Another thing that I'll throw out there, if you end up paralleling your ungrounded conductors, that's your hot conductors because you need more current, rather than go to bigger wire, you put more smaller wires together and run them in parallel. When you're running a neutral for that, the neutral size is at least 1 aught, and you have to put a neutral in every raceway or every cable assembly. You can't just go one big one in one raceway while you have the parallel ungrounded conductors in the others. It has to be the characteristics in 310.10h have to be consistent. Okay, so you would have a neutral conductor in every one of those raceways or cables. Okay, and you're going to count those if they are current carrying or they qualify as current carrying. Then you're going to, and we're going to talk about that here, then you have to count them, right? Okay. Again, the branch circuits, when you're dealing with the same concept, they're not usually installed in parallel because, again, the 1 aught is the minimum size conductor generally permitted to be installed in parallel. So just kind of things to remember, okay, in your application. But as we talked about, when you're dealing with a multi-wire branch circuit, or you're dealing with like service conductors coming in, or you're dealing, again, a lot of times that single phase service or remote distribution panel where that neutral is truly only carrying the unbalanced current from either line A or B, then you would not count that neutral as a current carrying conductor. Okay, so I kind of covered that one is about as much as we need to. Now, let's move on to B. Now, B, I'm going to read it, and then we'll discuss it. It says, in a 3-wire circuit consisting of 2-phase conductors and a neutral conductor of a 4-wire 3-phase Y-connected system. That's important, okay? It is 3 wires that are deriving from a 4-wire 3-phase Y-connected system. So important to remember, we're talking about a Y-connected, not a delta, a Y-connected system. Now, it says a common conductor carries approximately the same current as the line to neutral load currents of the other conductors and shall be counted when applying the provisions of 310.15 B3A. Now, I can't really get any more detailed than that. If you know, and the engineer who's designing the system should make it clear. Okay, it should be crystal clear that if it is a 3-wire circuit system, okay, consisting of 2-phase conductors and a neutral, all right, and of course it could have an equipment ground as well, but it is dealing with 3-wire, 2-phase conductors and a neutral, and it's deriving from a 4-wire 3-phase Y-connected system. If they're doing that, then that neutral conductor is going to carry approximately the same amount of current. So let me give you an example. If I have a Y-connected system and I have a black, red, blue, and I'm only going to use the black and the red, and I'm going to go to the center point of the Y, that's going to where I'm going to get my grounded connection, which is theoretically connections to Earth, as a reference, and that's the point that's required to do so. And when I do that, I'm running 3 conductors out, a black, red, white. Okay, but I'm not running the blue for whatever reason. If that's the application, and I have 10 amp loads, 2 separate 10 amps. I have 10 amps for the black, and I have 10 amps for the red. Then what happens is the neutral is going to count and carry approximately the same as the phase conductors. And if that's the case, then there's still some cancellation that takes place because you're not having 10 and 10 is 20 in this scenario, but you're still going to carry approximately the same current. And that's what it tells us in 5B. So rather than lose brain cells over it, I tell electricians all the time, don't overthink it. The key here is to qualify the system. Find out from the engineer or whoever's designing it, hopefully it's on the blueprints, am I dealing with a 3-wire circuit which has 2-phase conductors and a neutral deriving from a 4-wire 3-phase Y-connected system? If that's what I'm doing, then I know that I need to treat that neutral as a current carrying conductor, and I need to make sure I'm sizing it accordingly. All right? And so, yes, the adjustments that you're going to have to take place or for the number of current carrying conductors could come into play. Obviously, the ambience as well could come into play because also should remind you that when you're doing the neutral and the unbalanced currents, when we talked about 5A a minute ago, and it says you didn't have to consider 310.15 B3A, that's an adjustment factor for the number of current carrying conductors. You're always going to have to worry about the ambient temperature, okay? You didn't get a free pass on that, okay? So be very aware of that, okay? I just want to make sure I went back and reminded you of that. All right, so this one is pretty clear. You have to know the system. And again, it's very much driven to a Y system, okay? Now, that one's pretty cut and dry, and it does state that you're going to have to count as a neutral, okay? So, again, if you don't have more than our scenario, we simply had a black, red, and a white, then it still wasn't more than 3 current carrying conductors, okay? But it could come into play if you're paralleling and things like that, so just keep that in mind. All right, the next one we're going to talk about is where you are going to run the 4 wires. Let's say, for argument's sake, the black, red, blue, and the white. All right, and let me read it to you, and then we'll kind of discuss it. It says on a 4-wire 3-phase Y circuit. Again, we're talking Y here. Okay, it says where the major portion of the load consists of nonlinear loads. The major portion, okay, consists of nonlinear loads. Okay, So major portion would be over 50%, or 51% or greater of the loads consist of nonlinear loads. Okay, so the next question, ultimately from people I get, they say, Paul, well, why don't you tell me what a nonlinear load is so we can move from there? Well, nonlinear loads would be things like electric discharge lighting. That's the fluorescent lightings, and most of these large buildings have a lot of this fluorescent type lighting. Mercury vapor, high pressure sodium, a lot of data processing. So you have a lot of computers in a building, things like that. Again, you have to identify what system it is. Again, we're talking a Y system and where this comes into play. But if you're building, you're doing the service, and you're doing these calculations, you definitely need to know whether or not you're dealing with these nonlinear loads. Motors, for example, are a linear load. Okay, I kind of say there, what you see is what you get kind of loads. But the stopping and starting and the fluctuations of these non-linear type of loads have what's called an erratic waveform. It's not a smooth sinusoidal transfer of power. It is all over the place. It disrupts the amount of current. It doesn't cancel out very well. And because of this effect and the elevated potential for harmonic currents, and the third harmonics are the worst, then what happens the third, the fifth, things like that, a third, the fifth, the ninth, the 12th, all those type of things. What happens is the neutral doesn't cancellate out, or the phases don't cancel out this neutral. It becomes cumulative, and it becomes a problem. And so you start burning up transformers, you start overloading neutrals. You don't take those things into consideration, then that's when you get a lot of those neutrals we see in buildings that it was a white conductor and now it looks brown. It's because they moved around these loads and they weren't real cognizant of what they were doing. They just popped them all in there, or somebody's come in there at a later date and changed things, and now you have this issue, whereas you have accumulatives, or they didn't take into account the amount of current that would be traveling, or the harmonic effects. Now, there's some things that you can do in the design stage that I tell people. There's many things you can do. For example, I could have what's called a K-type or K-rated transformer that will basically try to cancel out these frequencies or reduce them, because, again, the amount of current in the waveform, it becomes a frequency issue, and again, above our discussion today. But what it does, just remember that we don't have that effective cancellation of neutral current. It becomes erratic, and because that cancellation doesn't take place, it almost becomes additive, if you will, the easy way to explain it. And this is something that the design engineers have to take into consideration. They really need to know. Now, as me as an electrician, I need to make sure I get that information from the engineer, and hopefully they put that on the drawing, or they've already taken this into consideration. Sadly, they don't always take that into consideration. So a savvy electrician or a project manager will always double check that, make sure they know what they're dealing with. But again, if you have a lot of nonlinear loads in a building, you really, really, really need to take that into consideration. Okay. Now, branch circuits and feeders is where we see it the most, and they supply these major nonlinear loads. Again, the current on that neutral can be as great as much as 2 times. Okay, 2 times that of the current in the ungrounded conductors. Okay, it becomes cumulative or additive, and that is a serious problem. So another way that people combat this is they go with what's called a super neutral or an oversized neutral. Whereas they know this is going to happen, they know that neutral conductor is going to carry a lot of current, so sometimes they will double the size of the neutral in an effort to make sure that it can carry a larger amount of current. So if you ever get into an application where you notice that the neutral is larger than the ungrounded conductors, and you do a little looking around, the chances are you're going to see that you're dealing in a situation where you have the harmonics involved in it, okay, and that's what's taking place. So that's what you might run into. All right, but there's other ways. Again, like I said, oversized neutral, K-rated transformers. All of those are recommended for that situation, and that can help rectify the problem. Reach out to the engineer and designer if you think that's going to be an issue. Okay, so that's one of the aspects that we saw directly in C when you're dealing with the nonlinear loads, which can result in harmonic currents will be present in the neutral conductor. Now, if and that's the case, and again, we're dealing with a major portion of this, then the neutral conductor shall therefore be considered a current carrying conductor. And again, that's what brings in the adjustment factors in 31015B3A if it needs to be applied if you have more than 3 current carrying conductors. And again, if that neutral comes in our case, if it's a black, red, blue in there, and then we have a four-wire Y system with nonlinear loads, a major portion of that takes place. If that's the case, then that fourth conductor, current carrying conductor, will be the neutral. And that has to be taken into consideration. And there's a good chance that depending on the amount of nonlinear loads that you're dealing with, it could carry 2 times the ampacity that any of the phase conductors are carrying. Okay, so always keep that in mind in that design. All right. So at the end of the day, if you have a single phase 3-wire circuit, as we talked about earlier, just a single phase. And in that scenario, then we've got 10 amps on the black. We have 15 amps on the red. Then the unbalanced current is going to be 5 amps on the neutral. And obviously that neutral is going to quite less, and it's not going to provide an overheating process. It's going to contribute some heat, but not enough that has to be worried right now as far as the code's concerned. So you don't have to count that neutral as a current carrying conductor. All right. Now, again, some motors that you're dealing with will have, which would be a linear load. The motor deal would be a black, a red, and a white, a black, a red, and a blue, for example, 3-phase. And then, of course, it's going to always have an equipment grounded conductor because you get fault current, but you won't have a neutral. Remember, just to throw it out there, that you still got to count that equipment grounded conductor when it comes to raceway fill requirements. But you don't count that as a current carrying conductor. Obviously, it's an equipment grounded conductor. It's only going to carry current for a brief amount of time to clear an overcurrent device in a condition where we have a fault condition. Okay, so you don't have to worry about that application when it comes to that. Okay. All right, so that was kind of explaining 5A, B, and C when it deal with when we're dealing with what to count when it comes to a neutral conductor. All right. Now, we didn't want to really get into other aspects of it as far as current carrying conductors, except for I do want to talk about the applications of when you count the current carrying conductor when you have spares in a raceway. Okay. So we're kind of not going to talk about raceway fill, but if you're doing an installation now and you understand the other stuff fully, and you understand when you count that neutral when you're dealing with Y systems, and when you don't, when you're dealing with a single phase or a three-wire circuit, or when you're dealing with a multi-wire branch circuit application. Now I kind of want to talk about what happens if when else do I count the current carrying conductors in this application? Not so much just the neutral, but now I'm going to kind of move into just counting conductors as current carrying conductors. All right, as we transition into that, I do get questions that come to me from time to time. One of the questions they ask me, Paul, what if I'm dealing with a section of raceway that's 24 inches or less in length, and then I direct them to 31015B3A2, and what I tell them is if that's the situation, then that short section of raceway, then I'm not required to count if the conductors are installed without maintaining any spacing for 24 inches or less, then I don't apply the ampacity adjustment. It's not required for that small section. Okay? That's just kind of throwing it out there. People ask about that all the time. And again, I'm kind of shifted from neutral to we have a good understanding of neutral conductors. Now I'm trying to talk about what other ones do I not count as qualifying as a current carrying conductor. Okay, so basically I don't have to apply the application of 31015B3A when I'm dealing with a small section like that. Okay, and where that is found, again, is let me get it to it. 31015 B3 I want to read you the whole piece if I can. Yeah, it's 31015 B3A, and you'll go down it and you'll see where it talks about the small sections, and that would be number 2. And it says adjustment factors shall not apply to conductors in raceways having a length not exceeding 24 inches. Okay. So I didn't want to spend this video talking about all of the adjustment factors, but again, just because I get that question a lot, if it's 24 inches or less, then I don't have to apply the requirements for the adjustment factors that are in 31015 B3A. Okay. Now, I still have raceway fill, and since that constitutes a nipple, I want to make sure that it don't exceed 60%. Okay, Chapter 9, you can go down and read all that in the code and understand that what the percentage fill is for the nipple under Chapter 9, Table 1, actually. So, what else are we going to go to here? Just so I can cover some of these topics. Since I already went down that road, might as well finish that road real quick. The next application we talk about, let's see here. I want to make sure I cover all the little stuff. Travelers. I get that from time to time. People asking about the travelers. Now, you're not required to count the non-current carrying traveler conductors in a 3-way and a 4-way switch arrangement. Now, if you're not familiar with that, NMB or even in applications where you run them in raceways, where only one of the travelers is carrying current at any given time from point A to point B, then I don't have to count. So only one conductor needs to be counted when determining the ampacity adjustment factors. Okay, I don't have to count both in a traveler scenario. Okay, so but if I'm doing this in a raceway, I'm only not counting it as a current carrying conductor. I'm only counting one, because any given time, depending on the 3-way or 4-way switching, only one of them at any given time is going to carry current. So, but it still takes up space in a raceway, right? If I'm doing a raceway application when I'm doing a 3-way or 4-way. Then if that's the case, then I still have to count it when I'm doing a raceway fill calculation. So I get that question. I'm just trying to throw some things out here to round this video to 45 minutes. So I'm just throwing you some stuff. All right, so that's something that you do have to take into account. Now, lastly, we talk about spare conductors. You do count all spare conductors. These conductors are required to be counted as they occupy space in the raceway and may restrict current carrying conductors from dissipating heat into the ambient. Okay, so what are we talking about with that, and where is it in the code? So I simply will draw your attention to table 31015B3A for adjustment factors, because we're talking about extra conductors, spare conductors as well, and then we'll lastly touch on that and move on and end this episode. When you have more than 3 current carrying conductors, you'll notice that under that table up there where it says number of conductors, it has a little 1 above, right next to the conductors in the table column to the left. And you go down to the note. Now, this is very much applicable note. It's not an informational note. It applies. And notice that it says, look, the number of conductors in the total number of conductors in the raceway or cable, including spare conductors. Okay? It says the count shall be adjusted in accordance with 31015B5 and 6. It says the count shall not include conductors that are connected to electrical opponents that cannot be simultaneously energized. And that's what we talked about, 3-way and 4-way. Again, I don't have to add but one of them. Okay, I don't have to add them both. Okay, in that application. All right, because neither one of they're both not going to be energized at the same time. Okay, so but I still count. Now, when it comes to raceway fill, I count them both because it takes up space. But when I come to current carrying conductors, I don't. At any given time, it might be a current carrying conductor, but they both aren't going to be at the same time. If you would, you'd have a dead fault, and of course, nothing would work anyway. So here's how this applies. But most importantly, you do include any spares you run in there, because at any given time, obviously they take up space, so you're going to count them as a raceway fill, obviously. But they also could potentially carry current, and they could potentially be current carrying conductors, so they have to be included, so you're going to count them as current carrying conductors. Okay. Obviously, if they're neutrals and they're not to be designated as current carrying conductors based on what we just previously talked about, then you wouldn't count them. Okay. But that's kind of gives you an overview of what you count and what you don't count. Just remember, you're going to spend a lot of time, anytime you're on an exam or you get lost and you want to know whether something is considered current carrying or not, understand the key topics in 31015B5, whether or not you're dealing with the unbalanced current, if that's stated in the question, whether or not you definitively know that you're dealing with a 3-wire circuit that is derived from a 4-wire 3-phase Y connector system, and you know you've got 2 phase conductors and 1 neutral, then that's going to kick in the next part of that question. Am I dealing with a major portion of, is that the scenario, or is it a pure 4-wire 3-phase Y circuit where I have a major portion of nonlinear loads that's going to generate harmonic currents? And do I have to take that into consideration? And on an exam, it should give you the details. In the real world, simply seek out the engineer to determine. But again, showing you how that works, and I gave you some of the other aspects of what gets considered a neutral or not, or what gets considered a current carrying conductor. Obviously, that's a big topic. I could go into another podcast with those other things like groupings and things like that. But I wanted to just kind of touch on the concept and the fact that when you're dealing with the number of conductors, how you apply the note 1 to the table in 31015B3A, and that tells you that those spares are counted, not just for raceway fill, but also are going to be counted when it comes to the number of conductors to apply this adjustment factor. It states it right there in the note. A lot of people want to say, well, there's spares. Okay, there's spares, and I don't have to take them into consideration. Not true. You are going to take them into consideration as current carrying conductors if they're in there. Okay. I mean, the easiest thing to tell people is don't get caught into the semantics of saying, well, they're not current carrying because I've got loads on these conductors that are in there. They're just spares. I don't want to count them. Well, don't let that bog you down because the code's clear. You're going to count them. Now, ultimately, they're not really carrying current at the time. They're just sitting there. Okay. But they could at any given time, and there's a reason you put the spares in there, and so they could count. Now, if down the road they qualify as a neutral for whatever reason, again, realizing that they would have to be 4 and larger in order to be able to take a white and re-identify it or something like that, which in a raceway, that's not going to be something that you can typically do. Okay. At the end of the day, whatever the color scheme might be, then you get away with counting it. And if it falls under 31015B5, which is a neutral, then you don't count it, or B6, which is an equipment ground, then you don't count it. You count it for raceway fill, but you don't count it as a current carrying conductor in order to be able to come up with a percentage value to what we say derate the ampacity of a conductor. All right. That's a lot of information. Hopefully you got something out of that. Hopefully I did not confuse you. That is not my intent. But if I did, I apologize in advance, and you can always email me at info, I-N-F-O, at masterthenec.com. Or you can send it to info at electricalcodeacademy.com, or maybe the easiest thing to do is just go to our website, click on the Contact Us link, and there you can type whatever you want in that form, and you can send it right there, and it'll come in on the form, and maybe the easiest way to do it. All right. Till next time, folks, hopefully you got something out of that. You didn't get too bored. Until next time, stay safe, and God bless.
Every day, the future's getting closer. Every day, the future's looking bright. Every day is another beginning.